We've all heard that what goes up must come down. But have you ever stopped to wonder why everything seems to fall at the same rate? Or what that number, 9.8 meters per second squared, actually means? Well, today we're going to get to the bottom of one of the most fundamental constants in physics, the gravitational field strength, which we all know as G.
So here's the game plan. First, we're going to ask, what is a gravitational field, really? Then we'll figure out how we get that famous 9.8 value right here on Earth. From there, we'll see how gravity changes the higher up you go. We'll apply our formulas to stuff all over the solar system. And finally, we'll boil it all down to the two key things that determine the strength of gravity anywhere.
All right, let's dive right in. Section 1, gravity's force per mass. See, to understand G, we first have to understand the space it lives in, the gravitational field itself.
So what is gravitational field strength exactly? You can think of it like a map of gravity's influence in space. At any single point, G tells you how much gravitational force would pull on every single kilogram of mass you put there. It's literally the force per unit mass. And here's the really cool part. This value is also the acceleration an object will have if you just let it go at that spot.
Now, how do we actually calculate this thing? Well, this is where the genius of Isaac Newton comes into play. He gave us two powerful and equally correct ways to describe the force of gravity, and we're going to use both of them to unlock the meaning of G.
First up, there's the big cosmic perspective, Newton's law of universal gravitation. It says that the force of gravity between any two objects, let's say the Earth and a little test mass, depends on this universal constant G, the mass of both objects and the distance between their centers. And pay close attention to that distance being squared on the bottom. That's huge. It means the force drops off really, really fast as you move away. The second perspective is the one we feel every single day, weight. The force of gravity on an object is just its weight, which we can find by multiplying its mass by the local gravitational field strength, G. Simple as that. Okay, section 2, calculating G on Earth. So, we've got two different equations for the exact same force. What do you think happens when we treat them like two sides of the same coin? Well, as you're about to see, this is how we can derive the exact value of G.
Because both formulas are describing the exact same gravitational force pulling on our test mass, we can just set them equal to each other. This one simple step is the key to this whole derivation.
And now for the magic moment. Take a look. Notice how the mass of our object, m0, is on both sides of the equation. It just cancels out. Now, this is a seriously profound insight. It means the acceleration an object feels due to gravity has absolutely nothing to do with its own mass. This is exactly why, if you ignore air resistance, a feather and a bowling ball will hit the ground at the exact same time. It's the planet's properties that call the shots, not the object's.
With the object's mass gone, we can now plug in the values we actually know: the universal gravitational constant G, the mass of the Earth, and the radius of the Earth. And when you run those numbers through a calculator, what pops out? You guessed it, that famous value, 9.8 meters per second squared. See, it's not just some random number. It's a direct consequence of our planet's mass and its size.
And here's a fascinating bit of history for you. Newton published his law way back in the late 1600s, but it took over 100 years for anyone to actually measure the value of G. It's an unbelievably tiny force to measure. Finally, in 1798, Henry Cavendish performed this incredibly delicate experiment and nailed it. And by doing that, he basically weighed the Earth for the very first time.
On to section 3, gravity's strength with altitude. Okay, so we've got G figured out for the surface, but what happens as we move up? If you climb a mountain or launch into space, does gravity just switch off?
No way! Looking back at our formula, the only thing that changes as we gain altitude h is the distance from the Earth's center. It's not just the Earth's radius anymore, it's the radius plus our height. And since that whole term is squared in the denominator, gravity doesn't just get weaker as we go up, it gets weaker faster. It's that classic inverse square law at work again. This table really puts it all into perspective. I mean, look, at the top of Mount Everest, G is basically the same as it is at sea level. But here's the kicker. In the orbit of the old space shuttles, 400 kilometers up, gravity is still about 90% as strong as it is on the ground. The reason astronauts feel weightless isn't because there's no gravity. It's because they and their spacecraft are in a constant state of freefall around the Earth. It's only when you get way out there, to the altitude of communication satellites, that the value of G really starts to drop off.
All right, section 4, applying the gravity formula.
Now, the real power of this equation is that it's universal. It doesn't just work for Earth. We can apply it to any celestial body you can think of, from meteors streaking across the sky to massive distant planets. Let's try out a couple of examples.
So let's think about a meteor, a shooting star. They usually light up at an altitude of about 120 kilometers. If you plug that height into our formula, you find that the acceleration due to gravity up there is still about 9.4 meters per second squared. That's incredibly strong. Earth's pull is very much still in charge at that height.
So what about other planets? Let's take a look at Jupiter. It is an absolute giant, both in mass and in size. If we apply our general formula for g, that's big G times the planet's mass over its radius squared, we get a surface gravity of about 24.8 meters per second squared. That's more than 2.5 times the pull we feel right here on Earth.
Okay, time for a little thought experiment. Imagine we discover an exoplanet that has 5 times the mass of Earth, but it's also got twice Earth's radius. What do you think? Would its surface gravity be stronger or weaker than ours?
Let's break it down. We know g is proportional to the planet's mass divided by its radius squared. So on top, we've got 5 times the mass. But on the bottom, we have 2 times the radius, and that whole term gets squared, which gives us a factor of 4. So the new gravity is 5/4, or 1.25 times the gravity of Earth. It's a great reminder that both mass and radius play a huge part.
And that brings us to our final section. What truly determines g? So after all of this, what does it all boil down to? What are the only 2 things that actually define the strength of a gravitational field?
It really just comes down to 2 things. First, the mass of the main body, the planet, the star, whatever is making the field. More mass means a stronger field. Second, the distance from the center of that body. The farther you get, the weaker the field becomes. And what's not on this list? The mass of the object in the field. It simply doesn't matter.
So, I want to leave you with one final thought to chew on. If astronomers discover a distant exoplanet and they measure its surface gravity to be exactly 9.8 meters per second squared, does that mean they've found Earth's twin? Well, not necessarily. All that number tells us is that the planet's ratio of mass to its radius squared is the same as ours. It could be a tiny, super dense, rocky world, or it could be a gigantic, fluffy gas planet. It's a perfect example of how a single number is often just the beginning of a much bigger, more interesting story.